STM and STS also some mistakes. Please.
Yeah, thank you. So today I want to add a new ingredient, and these are bosons. And you might wonder what bosons has to do with STM. We are actually doing spectroscopy with fermions. But I will show to you that actually we can see photons. And then with the help of electrons. And then naturally also conventional superconductivity arises. It's the interplaying forms of electrons. And I'm showing you some unpublished data. Not because there is no published data. There's heaps of published data on this thing. But I like to speak about things that interest me more at the moment. And these are naturally things that are not published. So I want to give you a view to things that happen at the moment, just because I'm more interested. But a short recap of last lecture. So we looked at some historical ones, how the STM was invented and how we can compute the tunneling current. And there were some severe approximations. Bardeen model, the two electrodes can be solved separately and their interaction does not change the states. And first order perturbation theory only, and it neglects the further transport of the electrons. If you lift a little bit the constraints on the overlap of the wave functions, then the interaction of the systems leads to change of the wave functions of the forces. And then we also went to K-space for Fourier transforming. And I showed you that we can do similar things in photon emission. We can reconstruct the dispersion. But with a nice addition that we can not only see occupied, but we can also see unoccupied states. And we extended the transport, so beyond the tunneling junction, we asked where does the electron go further. This brought us to ballistic electron microscopy and also to the dynamical Coulomb gate. But also it gave us noise. So we also could make a statement about the current noise. Then I reminded you that what we see, strictly speaking, is not the density of states, but we measure the addition of diffraction spectrum. We actually physically add an electron to the system or remove an electron to the system, which can have consequences if the sample is small, Coulomb gate. And I gave a very brief introduction to tunneling to superconductors, and there was a discussion yesterday about noise. I showed just one figure, and there was the question, are there more papers? And indeed there are more papers. So the first paper on this subject is this one. You can look it up. Unfortunately, this paper is a bit strange because they also saw 3E, 4E, 5E, 6E particles. 6 additional particles, so this is maybe the first paper in the noise business, but it was not really understood. But then planar junctions with niobium, so that was a question, is this reliable data I showed you? This is the data from Nature from 2000.
This is not below TC.
This is below, everything I showed is below TC. Was below TC. Below. I took the figure from below TC. Yes, so nothing is wrong. And also with simple superconductors, just lead, Milan did an experiment where you can see the same thing, also below TC. Above TC is actually a big question. Do Cooper pairs exist above TC? And this is under dispute. So the figure I showed you last time was not in the range of the dispute. So this was a disordered superconductor, which is believed to be that the superconductivity breaks down not by breaking up Cooper pairs, but by losing coherency. And okay, you can discuss that with the authors. I'm not the author of the paper, but still I think there is potential to look at unconventional superconductors. This noise spectroscopy. Anyhow, today I want to extend everything to inelastic processes. So we will look at inelastic tunneling spectroscopy. That's the technique to actually see bosons. This will naturally bring us to the very new problem of superconductors. And then we look a little bit at vortices, carbon-energy states, just do some spectroscopy there. And then I will share some recently published and unpublished results from conventional superconductor lab, which surprised us very much. And I'm so excited about it. I want to discuss this, so I should. So what is inelastic tunneling spectroscopy? So far, we have assumed that the electrons, let's say from this metal electrode, will tunnel from occupied to unoccupied states and reside on the other side of hot electrons. So we did a ballistic theory, there's no loss of energy. But already in the 60s, tunneling spectroscopy of Banach tunnel junction showed that there's another process happening. Especially this insulator is aluminum oxide and it's dirty. So you prepare your aluminum and oxidize it in the vacuum chamber. The vacuum chamber is not clean. You have, for example, pump oil in the system. There are some molecules inside this barrier. So what can that change? Now they are localized states that would not contribute too much to tunneling current. But what can happen is that the tunneling electron here can interact with this local defect and give parts of its energy. And the excitation is in form of a vibron, or a phonon. The vibron is a localized phonon. It's a molecular vibration. And there's some kind of matrix element to it. This process is proportional to this matrix element. So that means the electron loses some energy in this collision with the molecule. The molecule starts to vibrate with h bar omega. And of course, the electron has to lose this energy, h bar omega. And then you get another final state somewhere below the bias condition. Now, interesting is how will that show up in your experiment. Now, first of all, the final states of the electrons here are different in energy. It means if you compute this, quantum mechanics, they don't interfere. So you can treat that as two independent channels of transport. An elastic channel and this inelastic channel. But for the inelastic channel to happen, the final state here for this electron must be unoccupied. So obviously this process cannot happen if the bias voltage is lower than h bar omega. Then this final electron state would be here inside the Fermi state. And the state is occupied. So you have a switch. If EU, EV, or the bias voltage energy is large enough so that the final state electron is unoccupied, this inelastic process will switch on. So let's take the simplest approximation. We have a linear constant density of states, and our ID curve is just a straight line for the elastic current. But once we hit with the energy, the vibron energy, the second channel opens, and again we get an additional channel, which is linear, because we have the same linear density of states, constant density of states here, and it will set on set the start exactly at this vibron energy. So we see a small change of slope in the ID curve. Or alternatively, you can compute the differential conductivity. So our assumption was constant density of states, so the ID is constant in this picture. So this part is the elastic differential conductivity. And once you hit the phonon energy, the second channel opens up. And this one is again proportional to the elastic current, because we end up again in this unoccupied states. And the height of this is then proportional to the square of this matrix element, for this elastic collision of the electron with the molecule. And you can go one step further. You can take the second derivative of the matrix current. So this step up will make a delta function exactly at the phonon energy. And the height of the delta function is given by this matrix element and the density of these phonons. So this is a simple approximation for this. And we only used that the density of states should not vary on the energy scale that we are talking here.
But we also assume that interaction between electron with when we see is not important.
Yes, so this one, I have no interactions here. So all my inelastic properties are happening in the barrier. I will lift this constraint later. So at the moment, this is the state of the art you find in the literature very often. And can we do that with SDM? And how big is actually this matrix of it? So the breakthrough paper is already quite old, 1998, from Wulfhekel, coming from surface chemistry. So they took this acetylene molecule, they put it on copper. Actually, it was copper 1 on top, but doesn't matter. You can see the crystal lattice here, and this is the SDM topography image of this molecule. It sits like this on the bridge side between the copper. Yeah, what do you see if you do tunneling spectroscopy? So now I will kill the lights again. I hope you don't fall asleep. Aha, okay. 1 is the spectrum on the copper, 2 is on the molecule. Sorry for my colors. 1 and 2. This is IV. I of E, hardly anything can be seen. They look almost the same, and if you make the difference of them on the noise level of SDM, you can see nothing. But you can increase the sensitivity by the login technique, the IDV. So this is the IDV of copper, this is the IDV of the molecule of copper. The difference is there is a bump here, which goes up by about 6, corresponds to 6.2% change of the differential conductance. Or you go to the second derivative, and then, oh, I missed one. 2 obviously, 2 is, I have to correct this. 1 is on the molecule, 2 is on the substrate. So on the molecule, the second derivative, you see a nice peak. And on the copper, you see nothing. So the difference gives you a very reproducible peak at 358 millielectron volts. And this happens to be the stretch mode of CH. So this is the vibron, and the hydrogen starts to vibrate along the bond axis. And this is really vibron, you can check. This is the nicest achievement also from this group. You can take normal acetylene, or you replace the hydrogen by deuterium, so the mass is different. Electronically, it's the same. And you repeat this experiment, and you see that this peak shifts to 266 millielectron volts, exactly as you expect from this change of the mass of the vibrating object, the hydrogen nucleus. And you can even that. So this is topography. Then I use ICS 266 millielectron volt. This is this peak here. You can see locally resolved. This inelastic peak in the second derivative. And on this one, you see it another energy. That means this one is the you see this one is the deteriorated, and this one is the ordinary hydrogen. So you can actually find out what are the nuclei in the systems by the vibrons. And one even more impressive work comes from the IBM group, Heinrich. He took CO on copper 111 and makes an example lattice here. And they identified the CO. The difference is that once it's 12 carbon or 13 carbon, and this is the second derivative of the tunneling current. And you see there are some peaks. This one at 0 is the negative multiplicate. And here you see actually the isotope shift. So that means you can by spectroscopy decide which one is 12 and which one is 13 carbon. And you can use lateral manipulation actually to sort this out. And you can make some images of 12 to 13 carbon and image that as some kind of image here. You see the contrast of the differential conductance for the same differential. So maybe a politically not correct comment. This is an isotope selection machine. You can enrich uranium by this very efficiently. Unfortunately, one atom takes a couple of minutes, so you cannot build an atomic bomb with this. So the Iranians are very interested in this. No chance. Okay. This spectroscopy has also the resolution. And now this is the second derivative of the differential conductance. Several Fermi functions enter. And if you compute the spectral spreading due to temperature, it's 5.4 kBt now. Elastic is 3.4, if I remember, 6 kBt, if I remember correctly. And also the modulation enters. This is the second harmonic now in the Lockheed continues. And we also have a different effect here. So that means the energy resolution is a little bit worse than in elastic tunneling. So far so good, so we can see vibrons and molecules. This is of course a nice thing for chemistry, but we are more interested in solid state. Actually, I could switch on the line again. What happens if we move this interaction point of the hot electron from the barrier into the bulk? Now, in most of the tunneling experiments, there are no molecules. This is a vacuum gap, so the vacuum has no vibrons. Fine, there will be no excitations. But I could, in principle, think that I can shift this interaction point into the system. The second electron. All the same story applies here. We have an elastic tunneling current and an inelastic tunneling current, which adds up. And we can see the interaction of electrons with bosons, phonons now, in our sound. So if that's correct, the second derivative of the tunneling current will give us information about phonons. Now, okay, I should mention that now in phonons, of course, vibrons only have an energy, and the eigenmode, which is localized, phonons are extended objects. They have a wave vector. So keep that in mind. And we don't measure this wave vector in our experiment. Is that possible? Should we see so? Of course, otherwise my talk will stop here. We showed that in 2015. It was actually quite a surprise. So you have to check a material which has a large electron phonon. If I ask you what should I use, you would say measure superconductor. Yeah, the electron phonon is large, so this is superconducting. Let's take lead. We try lead. And we put it on copper 111. Copper 111, of course, is not superconducting. And that means even if you go to very low temperature, the proximity effect of these small ions, which in principle would like to be superconductor, to the big normal conductor completely suppresses superconductivity. So even at T equals 0, okay, we can't reach T equals 0, but we measure at 700 millikelvin, this lead islands, the superconductivity of this lead islands is stretched. This is a normal conductor, but now it has a nice property of a large electron phonon. So what do we see? So let me explain a little bit about this image. So you deposit the lead at room temperature, and then you heat up the system a little bit. The reason is that we want to form islands. So what you see here are islands of different heights. These are monolayers. So most of the islands here are 8 monolayer, some of them are 6, 10, 12, and so on. And yeah, for some reason the odd numbers are not preferred. And you have what is called a wetting layer. So the substrate is wetted by a thin layer of lead and copper, which has a homogeneous thickness. If you take a spectrum on this thin wetting layer, we come to a spectrum now on bare copper. We see basically a flat, so this is the IBD, a flat density of states. So on this energy range, which is only plus minus 80 milli-electron volts, the dispersion is so small, the density of states is our material, copper doesn't change. So we can take the assumption, okay, we have a constant density of states. So all of the variations we should see in our spectrum cannot come from the elastic tunneling current. If you place your tip on one of these islands, you see something like a V-shaped thing there. And this was seen before by other authors, but it was never really interpreted correctly because it would be measurements without the too hot temperatures. If you now go to really low temperatures and measure the second derivative of the tunneling current, you get these kinds of curves. So on the red one, this is here. This is a certain thickness, 11 monolayer. You get 2 peaks, and you get some peak near 0. Now, all peaks at near 0, we know already, they come from the dynamical anomaly case. At the very low temperatures and very low electron energies, the state tunneled into this for a long time. You cannot add another electron. But away from that, we see 2 peaks, and these 2 peaks appear in all of the different islands with different intensity. The peaks are 4 and roughly 8 millielectrons. Now, what are the? This is the phonon dispersion. Dots are neutron refraction data, and the solid lines, the red line, actually is calculation, relativistic calculation for that. Fight. And from that, we can actually compute the density of states as phones. And you see there's a peak roughly at 4, and there's a peak roughly at 9. These are the Wulf singularities of the longitudinal and transversal phonon branches. And this actually fits our data very well. So it seems like we see phonons. I will come back to this. Okay, so it's a little bit strange thing that you would see in phonons in the tunneling current. This picture of the elastic and inelastic channel is maybe not the best view to look at that. There is another view to look at that, which is older than all of this, which one comes from Schiefer. So the question is, what are my electrons? So the electrons, solve whatever the equation of motion of the electrons in the potential, single particle approximation, or anybody or whatever TFT, you get a dispersion relation which describes the motion of the electrons, quasi-particles actually. But you neglected the lattice degrees of freedom. Now, if electrons and phonons can talk to each other, they will talk to each other. And that means the bare propagator of my electron will now be phonon dressed. So I can have a self-emission and absorption, and I get a self-energy correction for phonons. By phonons. So the electron propagator will be modified because it interacts with phonons. These are the dressed states. So my electron is not naked anymore. If it goes through the lattice, it will distort the lattice.
But it seems something completely different. I mean, one elastic and inelastic process are qualitatively different.
Yeah,
One is not equivalent to another.
Yeah. So the argument is the following: what will happen now? What will happen to the electrons? The dressed electrons will be heavier by the presence of phonons. This you can see in normal band structure. So we take photo emission data of some material. With high resolution, it goes into Fermi energy, this is linear expansion, AKF, and in the presence of phonons, you get a renormalization of the electron mass in the window of phonon energies. So the effect of mass changes. But as Schiefer showed you, the electron propagator, which is the delta function here, also gets side bands with phonons. So a native electron is dressed by phonons, and also in this paper, there's a discussion of how that has to do with inelastic processes. So either think about an elastic process, I go from the tunneling electron goes to the other side and creates a phonon, or I think about phonon renormalized density of states. And then all of the electronic bands will have side bands and phonons. So they add, and this is an elastic thing. So this distinction is maybe artificial, but you will see why it is. Yep.
Is it correct to say that the phonon renormalized spectrum contains sidebands because there's the main band which is just an electron surrounded by a cloud of virtual phonons, whereas the sidebands is the other way around, a phonon creating some distortions in the charge spectrum.
In other words, this self-kinetic correction has a real and imaginary part. Yeah. So you cannot just renormalize the mass, you have also renormalize lifetimes.
Of course, inelastic process means that phonon disappears somewhere. Right? It is a real process which is described by imaginary part.
Yes.
So,
So that means the imaginary part of the self-kinetic will play. Good. So it means nothing new here, but for some reason in inelastic tunneling this was not considered in tunneling experiments. This was always neglected in the simple density of states argument. In a better picture, you have to think in rest states, and then you get these inelastic processes for free, or you think in the two-step process, which is simpler for the experimentalist like me. Yeah, I can think in this picture easier, but the two pictures are equivalent, which I will show you. The link is the optical theory. Okay, good. What does that have to do with superconductivity? Now, superconductivity, okay. Now it's the slide, baby slide I put here. You know that conductivity suddenly runs to zero, as discovered by Honest, and then it was later found experimentally in 1911 and explained only in 1957. So that took a really long time to do that. And the reason is that all of these field theoretical arguments about what happens to stress states took some time to develop, and also quantum electromechanics. And the heroes are again Martin, that we know, Hubbard and Schäfer from this other paper I showed you. And the experiment and the theory both got the Nobel Prize. But you're mostly familiar with BCS. To explain this, we have to go beyond BCS. So BCS is, in simple words, electrons form a lattice that changes the charge distribution and will attract another electron. So it's attractive electron interaction mediated by the distortion of the lattice. And this was described in BCS theory by this kind of Feynman graph, which is a particular Feynman graph because it is an interaction for fermions on a point-like object, which is a non-retarded problem, and then you get this nice BCS density of states. This is not reality. This is an approximation for what's called the weak coupling limit. So the electron phonons are weakly coupling. If they are coupling more strongly, you see deviations from the simple BCS theory. And maybe the better way to look at it was formulated by Niederschlag. That's most likely what you think is BCS theory, but it's not exactly BCS theory. In this case, we have two electrons here, which scatter via exchange of the virtual phonon. So Fröhlich also described this in full detail, and Niederschlag did an approximation that is the scattering should not be Q dependent, but only energy dependent. So that means this coupling constant is a function of energy and not Q. And then this summation or integration of all of these phonons gives you the density of states and phonons. This looks like matrix element square times the density of phonons. That's all. It looks pretty much something like that in the elastic tunneling. This is what we wrote down just heuristically. What is the consequence of this? This quasi-particle peaks get renormalized. So these electrons, or these electrons, electron hole superposition states, they also get renormalized. First of all, the mass will change. And secondly, you get inelastic processes as well. So real part and imaginary part of the set. So in BCS you don't have this effect, this is neglected. And if you take high resolution spectra, this is Macmillan actually, I forgot the citation. This is lead. You can see there are some extra features here. They come from this renormalization of mass and the elastic channels. But anyhow, important is that in this simple picture, so we don't have a Q dependence. In this Leerspec picture, we can formulate a carrier loop function, which describes the interaction of electrons via virtual photon exchange. This is what expected to the square times the density of photons. This is the thing that drives activity. Okay, there's a certain resemblance here. So this is actually electron-electron spectrum by phonon. If I interpret this graph correctly, it's electron positron in relation to a photon in the recreation, but if we just turn around this and that, and turn around the time axis, then we have exactly a problem. The phonon is replaced by a photon. Or whatever this was intended to be. So the question is, this is our picture that we had in the elastic tunneling. The electron comes, emits a phonon. We don't measure Q. We measure only the energy. And actually we measure the square of this thing, integrated over Q. So in simple words, we take, now this, forgive me, this sloppy language here, this is an integral over this fiber diagram. Yeah, and we integrate over the phase space of this Q, which is this matrix element complex conjugated multiplied over Q. And then you immediately see we integrate over this Q here, which means we can also write this one. And this one is the imaginary part of this, this scattering graph. So this is an identity which is the optical theory. And the total cross section is this renormalization of the same energy, imaginary part. And this is the Leerspec function. So my statement now is we can measure this Leerspec function when the superconductor is in a normal state, directly when measuring the inelastic thermal current. And that's something that is actually a very nice statement, so you don't have to do very complicated, you don't have to solve very complicated data before you use the Macmillan inversion algorithm. So you take this curve here, the superconductor state, and the small deviations on the BCS density of states were self-consistently calculated with a spectral function and the matrix element, vary them until you get agreement. Very complex and not unique inversion. And my statement is this can be done directly in the normal state by measuring the differential second derivative of the tunnel current. So let's do it. Let's take this and take the second derivative. That is this function. So with higher energy resolution, you see this is not a V shape, but actually it's a step structure. We have a peak at 0. This is the dynamic homologate we can never avoid, and then again those two amorphous similarities. And this is the dotted curve is our spectrum, and the black curve is the reconstructed Leerspec function for Macmillan on the same element lead. And you see the agreement is pretty good. It's not perfect, maybe due to energy resolution, or to be honest, this is not exactly what happens because with STM you don't tunnel to all of the states at the same probability, but mostly in the states which have forward tunneling direction, so there's a little bit of weighting, and also maybe the matrix element is Q dependent. But in this simple approximation, the match is really nice. So our claim at that time in this PRL was that we can measure directly the Dirac function. Now back to our islands, 11, 12, 13, 14 monolayers. The Dirac functions go crazy. They are very different. I mean, the peaks are all at the same position, but the matrix element seems to be largely different. So 11 monolayers, a lot of electron scattering is happening. And on 14 monolayers, it's much reduced. Yeah?
Yes. On the picture C on the left, there is this tail on the left which goes up.
Here,
Yes.
this is the dynamical component.
Ah.
So this is a problem that we have with all of the tunneling experiments. If we tunnel to states which are very close to the Fermi energy at very low energies, at low temperatures, and we need energy resolution, these states live long. Yeah.
Yeah, but on the other hand, in the middle, on the B,
There is
there's no
such states.
take a look at the middle plot.
In the middle of
First,
B,
yeah,
B.
and B, and then
B.
at the top. Oh, sorry, at the bottom.
Bottom.
Bottom right. Bottom right.
To the right.
Yeah. Yeah, there, and there's no column.
These are large counted sensitivity calculations.
Okay.
So weight functions, those are not data.
So this is our experimental data. We measure now the Dirac function on these different thicknesses. Red, blue, green, yellow is 11, 12, 13, 14 model layers. You see it explodes from 11 monolayer. You want to understand why the Dirac function explodes from 11 monolayers. I mean, it would mean that if the Dirac function is larger, TC of the superconductor should be largely enhanced. Okay, it's quenched by substrate, but we can engineer electron forming. Why can we engineer electron forming? You remember that lead or copper makes quantum well states. So these are the spectroscopic. This is a large energy range. So our assumption of constant density of states is not anymore fulfilled. And you can nicely see these quantum well states. 11 monolayer will be a Dirac function is large. The quantum well state, what edge counts to the Fermi energy. Now, what would that mean? I have a quantum well state, which is just above the Fermi energy. And now I distort my lattice by a formula. Then the quantum well state will shift in energy. So, at these conditions, phonons will largely redistribute the electrons here, because the density of states strongly depends on energy. That can enhance the electron forming. Stop the lattice, all of the electrons are reshuffled across the Fermi energy into this quantum well state. And this has been calculated by DFT calculations now for the same system, and again, we see a large increase in the Dirac function. So lambda is the electron forming coupling parameter, strength, and goes from 1.31 to 2.21. So D will increase TC. If this was not quenched, I'm saying it. So there is maybe a way to boost TC in superconductors by superlattices. Unfortunately, we are not growing superlattices. Yeah.
I need two questions. One is a simple one. So why do we expect the phonon spectrum to be discretized? Is it because of finite size? Is this the single?
No, phonons are not discretized. These are electron sectors.
No, I mean, let's say in the right bottom point.
Here.
Yeah. So why do we expect this kind of structure?
So there are longitudinal and longitudinal transversal phonons. This is the phonon density of states.
Okay.
Times this matrix energy.
Okay,
That's assumed to be, for example, constant energy. So this is the calculated Dirac function of theory.
Yeah, okay.
And there is a change in the coupling constant when you change the thickness of lead. Just because the effect of the phonons to distort the lattice is different, or depends on the thickness of the layer, because there are quantum well states. So if you are in between two quantum well states and you distort the lattice, hardly anything happens to the density of states. They are principally zero in the extreme case. And if you are at the border here of a quantum well state, you change the length parameter, and then the dispersion changes, and the quantum well state will actually shift back and forth to the Fermi energy, which means you scatter a lot of the electrons. This was our argument. This is a naive experimental thinking, and you get something similar in DFT. Yeah.
You question the
Yeah.
you just left
So you could, in principle, take bulk lag and go above TC, but the energy resolution of the inelastic spectroscopy will kill the sensitivity. So we are like energy resolution of, let's say, slightly below a milli-electron volt, and if you go to 4 Kelvin, then it will be more than a milli-electron volt. You wash this out. But you can create it with a magnetic field, of course. So this was the beginning, and now let's do exactly like you said. We do it by a magnetic field or whatever. So this is our picture. I see it. We are tunneling now into a superconductor, into the quasi-particle states, not in the gap. And we have a renormalization of the electron mass, and we have lifetime argument. You have remission of photons. So there are two things happening. You get, if you calculate the second derivative, two things happen. The renormalization of the mass gives kind of a swing, which is, I think, the blue curve, and the inelastic one contribution to the current is the green curve, and black is the summation of both. Then you change the mass of these particles, so the density of states of the electrons, like change in the superconducting state, and also the inelastic channel opens. So we can do this experiment. This is maybe the IDV in the normal and the superconducting state. You see these steps, not very nice here. Sorry for the quality, but lead and silicon is not as nice as lead and copper. And in the superconducting state, you see these renormalization peaks, which are at 5.3, 9.4. Actually, this is shifted by the flat. All of this was happening here. The inelastic part is shifted, of course, by the superconducting gap. And also the mass of the electron is renormalized. And the density of states is shifted by delta. So these peaks are the same peaks as we saw before, but they are shifted by delta. So the superconducting case, our experimental data is red. There are two contributions, elastic and inelastic. You can add them up to the total. And then you can see the agreement is kind of okay. But all of the peaks are actually shifted. These are the phonon energies by delta. All of these things are shifted to the single particle spectrum, which is shifted by delta. And the deconvolution is more complicated. And it has been done before by Macmillan. I won't have to repeat that part. Okay, so far so good. This brings us to superconductors, and maybe they are important for you. So we want to, I want to talk a little bit about superconductors. So you know there are two types of superconductors, type 1 and type 2, which can be seen when you take the energy landscape with a variable order parameter in the field. So if you go to what you see, order parameter, if you apply magnetic field, you get a phase diagram. And type 1 actually is the Meissner state, normal state, and type 2 has the Meissner state, the Poisson-related, so the flux, quanta, plus vortices, and the normal state. And the decisive parameter is the interface energy between the superconducting normal state or this ratio of the normal critical value is roughly 0.7. So if it is smaller 0.7 of type 1 superconductor, if it's larger than 0.7 of type 2 superconductors. So the phase diagram looks like this. I switch on the magnetic field. If it's very high, it's normal. If it's low, zero field, then it's superconductor. And type 2 superconductor is via Microscopy lattice. Now, the type 1 superconductor does not directly go from here to here. That is actually wrong. It's written in a textbook almost like that, but it's from infinitely extended superconductor. Now, there is no infinitely extended superconductor. You have always finite sum. So actually, if you ramp up the magnetic field, the field lines will go around your superconductor until eventually the sample becomes at some point normal. If it's normal, the flux will become collected through the normal part, which means I reduce the flux onto the superconductor parts. And that means I get a two-phase diagram of large superconductor and large normal domains. This was actually solved by Wulf. It's an understatement. And the reason is the minimization has to be done also not only with respect to this order parameter, but also with respect to the straight field and the magnetic straight field. So the magnetic field energy has to be taken into account, and this is similar to magnetic systems, which will split up into domains because they want to reduce the magnetic straight field. So here we reduce the straight field of the ideal diamagnetic properties of the superconductor. So we split up into large domains of normal superconductor. And there are some superconductors here. Type 2 is anything like an iobium. Most of the elementary ones are type 1. But you can think of this also in terms of vortex interaction potential. So here we have exactly one flux quantum in each of the vortexes, and the vortexes repel each other. They don't want to form a large vortex. And here there's an attractive interaction between the vortices, so the vortices will collect into a very large domain of normal material. So the difference is maybe also vortex-vortex interaction energy. So let's take one of these two superconductors. Two superconductors, iobium and Kelvin. There are many examples, so I picked two. One from my own group, which is just actually it's not about superconductivity. This is just a characterization of our instrument. We took a bike iobium crystal from Kelvin, this is topography, and we sit with a differential conductivity outside the gap on the quasi-particle peak, and now measure as functional position the differential conductivity where we have applied a magnetic field. So if it's superconducting, there's a large differential conductivity, which is color-coded white. And if we are on a vortex where the order parameter collapses, the material becomes simple towards normal. This Williams peak will go down, our differential conductivity will go down, and we will see the black capsized. And this is what you see. You can actually map now these vortices with STM very nicely. But we are not the first who have done that. Maybe the pioneering experiment is much older, tested this, for example, on selenite. Very nice picture. But has already realized something else. The gap. So this is a plot of the spectrum as a function of distance from the core of the vortex. So you see the gap is closing. This material becomes normal when you go inside the vortex core because the density of the interaction is down to zero. But exactly in the middle of this vortex, there's a big peak of the differential conductivity at zero. What is this? Now you can think about an electron which sits in the unpaired electron which sits in this vortex. It cannot enter the superconductor near with zero energy because there's a gap. density of states which you expect here is not infinitely extended, it is in a round box. So you expect discrete states, and this has been solved before by Parodi and German particle. They predicted that there should be these unpaired electrons at the further energy, which form organized states because they cannot enter the superconductor. And it's actually topologically very interesting. Okay, now forgive me, I have not done this calculation, so my students have done this calculation. But in principle, you have to combine electrons and holes with a volume the general formalization of this problem and solve the Schrödinger equation. This is a very difficult.
So yeah, can you get that for one second?
Yeah.
So first of all, about pictures. So the left one,
Yeah.
A here to the bottom, this top of something.
This
Yes. So can you explain?
So this is our single crystal. We are under constant current feedback, and we see the atomic steps on the surface of this neighboring crystal. And at the same time, we modulate the voltage a little bit and measure with the login in IDV. And we sit with the voltage here. So if we are on a superconducting part, you see the slopes, the differential conductivity is high. If we are on a normal part, then the IDV is normalized to 1 here, it will be 1. So normal is 1, superconducting is under these conditions 2. 1 is larger than 2, so it appears bright in this image.
Okay.
We just map this quasi-particle.
Okay. And the right bottom.
Right bottom.
Yes.
Exactly the same.
I just can't see. So the axis.
Okay. So this is a position, and this is energy. So
Okay.
this is a tunneling spectrum of the superconductor.
So this is the same as A.
Yes.
Yes.
But now in this direction we have position. We go from the superconductor into the vortex and out again. So we see that this gap.
So this is literally like you get to the on the vortex.
Yes, they actually move on the vortex.
Wow.
And you see that the gap is closing, but you see this extra peak. And I want to explain this extra peak.
Yes, of course.
So,
wow. Okay.
So in principle, you expect a flat density of states. These are just density of states of normal metal, but keep in mind this is normal metal is only there in the vortex. So it's in a two-dimensional, no, in a cylinder. It's confined to a cylinder. So one direction is free dispersion, and the other one actually gets a particle in the box. And this is this problem here, particle in the box, and we want to solve the eigenstates. And to solve the eigenstates, you construct quasi-particles and confine it, and this is actually very, very difficult. The problem is there are really many, many states, because first of all, the z direction is free dispersion, and then the coherence length typically is a big thing. Yeah, coherence lengths in superconductors are lattice. Nanometers, 80 nanometers, 100 nanometers. And the crystal lattice is 0.2 nanometers. So that means a lot of states are involved. The box is big. So actually the level spacing is given by the superconducting gap to the square over the f. So it's a very narrow level spacing. Yeah.
Maybe that's because I missed the third lecture, but what's the typical size of the tip or the tip?
The tip, okay, the tip size does not matter as long as the tip wave function is an S wave function. Then we can contract the tip wave function to a point. Calculate the tunneling current, it is actually given by the density, local density of states of the sun in the middle of the last tip pattern, which gives it as a function. So the size of the tip in this simple picture does not matter. And all of the tips typically are atomically sharp. If you take a larger tip, you smear, of course.
So, that's the question. So, essentially, you're saying that they're atomically sharp.
Let me come to this. So this is position, and this is delta. Yeah, we have a vortex. So that means we have discrete states here. It's one particle in the box states. And this level spacing here is of the order of delta square over df. So it is very small. Yeah.
What limits the resolution of your image?
Lateral or energetic?
Energetic.
Energetic is if it's a normative, the Fermi Dirac function at that temperature.
So it's basically low
Yes,
temperature.
so that means this will always be much smaller.
That's why people can't actually resolve.
We cannot resolve those. Actually, what we will effectively see are bands. So this is the calculation. This is an exact calculation. You have those states here above the single particle states above the gap. And inside the gap, you have these Pauli region states, and they lie very, very close. They've actually made something like a band. So this is a single particle band in this box. Unpaired electrons in the box. Other unpaired electrons are outside this box. This is a calculation of this. This is Burgess here. Now, if we go out in energy, what is in this part is a round box. What are the states? Actually, since it's round, good quantum number will be the angular momentum of the electrons in this box going around. So actually, this is the dispersion which comes from the angular momentum, and the calculation can be done with the electrons are moving on these ring orbitals. And this one is very hard to solve. There's an Eilenberger formalism which is quasi-classical. I don't want to explain it too much, but this is what we can handle. And this is an example. If we have a spherical Fermi surface, then at E equals 0, we have a dot in the middle here. That means no angular momentum of this first state. And if we increase the energy, the angular momentum increases and we get a ring. So this is what is expected when you do a calculation without scattering. So these electrons have these quantum well states are well behaved. And you can learn something about the number of flux quanta in this system. So these are again exact calculations with odd and even flux quanta in this vortex. So we remind you, because of n equals 1, single flux quanta vortices. But if you would, by some means, change this number here, so that means the order parameter, the superconducting order parameter, winds up more than 2 pi. So m equals 1 flux quantum means the order parameter winds up by 2 pi, can wind up by 4 pi, principally, and so on. Then for every flux quanta, you get one of these branches going through the Fermi energy. Or if you make an image of the Fermi energy, you just count how many crossings you have. So if m equals 3, you have 3 crossings, 1, 2, 3. M equals 2 has 2 crossings, 1, 2. Or m equals 0, you have 1. So we go through here. 1, 2, 3, 1, 2, 3, 4. This is the index theory. So the topological index theory says m times finite vortex have m-fold winding, which become m-fold crossing of the bands at the 0 at the Fermi energy. Why am I talking about this? There are only vortices with one flux quantum. No, they are not. Why not? I mean, Ginsburg lambda theory says exactly there's 2 solution type 1, single flux quanta vortices of type 2, and large range areas in type 1. But this was, first of all, a thermodynamic approximation, so it's close to TC. Secondly, there was just one band. Now you can go to very low temperatures, far from TC, so this approximation about the free energy might not be a good approximation anymore. And typically, superconductors have more than one band. Most of the metals have lots of bands. So there's a... Yep.
Can you speak a little bit louder?
Yeah, so I repeat that. Yes. So the Landau-Ginsburg theory here is a expansion of the order parameter to finite orders, and it's valid near TC. And it has only one order parameter, which means I have only one band which becomes superconductor. The real world has maybe more bands, and we are free. We can go to very low temperatures, far away from TC. Now let's do that. Okay, this has been calculated in this paper. This is a two-band superconductor. And you find back type 1 and type 2, but the coherence lengths of band 1 and the coherence lengths of band 2 can be different. So one can be type 1 and the other type 2, in principle.
And K is kappa. Kappa.
Surface tension of your words.
I hope it's kappa. So this is 0.7, this was low Ginsburg theory, yeah. If you go closer to CC, there are only two solutions.
Yes, I mean, what this parameter is.
Lambda by xi.
Okay.
That's the ratio of the London penetration to the coherence length. And if you go lower in temperature, the phase diagram actually opens up, which is hysteretic. So it's, you can have hysteresis depending on the history where you go, with no single flux vortices, multi-flux vortices, single, and a lot of things can in principle happen. But this is only theory and nothing is actually seen. We work on lead, which has a kappa of 0.48. Critical value is 0.7. So maybe we are lucky. Lead. Now we go to really low temperatures, 35 millikelvin, T equals 0, while lead. This is the density of states, measured by STM. You see very nicely the hard gap of the superconductor, but you see two coherence links. It's a two-band superconductor because the Fermi surface of lead contains two bands, two distinct Fermi surfaces. And actually, by ab initio calculation, delta varies over two bands. So we have a delta 1 and a delta 2. And actually, delta 1 comes from this open Fermi surface. And delta 2 comes from the compact Fermi surface. So we have two compensates, not one each band. Okay, so this we showed recently. Now we apply magnetic field. That's type 1. Superconductor, you expect normal conducting areas and superconducting areas. So what I plot here is the differential conductivity at 1.3 millivolts. So 1.3 somewhere here. Yeah, so if we're superconducting, we have a peak. If it's normal, we don't have a peak. So the differential conductivity is lower here. The normal region is superconducting region here. And you can see the transition is not sharp because there's coherent lengths and all this stuff. But we also find these things. This 100 nanometers, this looks pretty much like vortex. Should not be there in type 1. But we have a two-band situation, and we are at very low temperatures. So this window opens for other phases. And we can look at these bound states, carbonic states. So what we do now is a local spectroscopy inside the superconducting gap. And we see this star. And if you look closely, you see another star here. And we can take the real band structure and calculate these particle remote states. And we expect from this band this kind of shape, nicely be found here. And so from the compact, or from the non-compact Fermi surface, we find a star, 6-fold star with a triangle in the middle. You can barely see it. This is at zero energy. So some people will say, wow, zero energy peak in the middle of a vortex. It's a minor Varna Fermi. No, it's not. Actually, it's just an ordinary carbonyl gem state. And they are very closely spaced in energy, and these carbonyl gem states are not at zero energy. So the carbonyl gem states, if you compute them, you remember this was kind of a band going through the Fermi energy. If you have a high resolution with one single states, you won't hit zero. Pairs, and there's no single one at equal zero. must be careful. Okay, we just want to be vigilant. Depends on the energy resolution, but no one has an energy resolution at the moment to distinguish these two cases. Here in the middle, and this spacing is so small. There is no instrument on this planet. Yep.
What is the state? You say it's not around more, something else. What is it?
So, marijuana would be its own antiparticle. There's zero energy. So, marijuana is here. And this energy spacing is delta squared over EF. So, it's a gap divided by the ratio of this superconducting gap and thermal energy. So, it's like 1/10,000th of the energy, roughly speaking. And we don't have the energy resolution to distinguish those two states. So I can't, so you would need something like nanokelvins with spectroscopic measurements to decide which one it is. But we can also change now the energy. And you see here all of the star arms split up. And this middle one makes a ring, and we can also simulate that all the stars. Here the star splits up, and this makes this kind of triangle, and this really see this. And from this dispersion of the states, we can find out that this vortex with M1. This surprise, type 1 superconductor has vortices. And we can map these states, how they close, how does the gap close. And you see for the two bands, pink and red, you can see that they're here, but they don't close together. They behave independently. So we have two common states, which in principle don't talk to each other, which means the scattering from one band to the other band is very low. Each of them has their own equations how to close in the presence of the magnetic field. So they are actually really two separate condensates. And I can show proof that to you by applying a magnetic field which is tilted on the surface in a special direction, which breaks the symmetry of the system. Now I don't have a round object, I have a tilted object at the surface, and you can see again the star, and you can see the other for one band, and for the other band you see the peak is now displaced. So by just changing a little bit the magnetic field, I can distort the vortex, and I can change the energy, you can say the splitting of those states. These are not sets of the origin states, and they are not centered on top of each other. Because the dispersion is different, and the applied magnetic field is strange direction which is not along the crystal axis. Or if you look at zero energy, we can take the path J or the path K. So the path J is going outwards, and we can see that one band actually closes when we go to the center here. The other band, the other gap does not close at this point. So here in this vortex, delta 2 goes to 0, delta 1 does not go to 0 in the middle. But it goes to 0 at this point K. So if we go from here to here, you can see this band 2 actually also goes to 0. So we have really band condensates. We have only one magnetic field, but we have two really band condensates. This is all published. Yeah.
But still, these two condensate should interact somehow between them. There should be some energy scale which characterizes this interaction.
Yes, let's look at that. So let me keep you a little bit more. I will come to that very soon. So the interesting thing is you find also vortices with MEV2, MEV3, and so on in 10. So we can count the number of arms here, and we can simulate them. So these are simulations of the isotropic Fermi surface, these are simulations in our case. So this ring structure becomes arms, and I can count now the arms instead of the rings, and it's a different index theory here. We should not count rings because our Fermi surface is not rotational symmetric, but we have to count arms. Yep.
What are those weird red lines across the...
Red lines are atomic steps.
Okay.
So this is an artifact, and I have to explain it to you. So we want to make sure that we measure the density of states That means we should not do the feedback when we only have count intelligent states. Because then we regulate the tip, depending if we are on a state or not, we regulate it away. So we stabilize the STM at a voltage above, far above the gap. We record the scan line, then we switch off the feedback. We go to zero bias, measure the IDV, and just replay the function, this position. And this replay, it works pretty well, except on steps. So you get some artifacts on steps. So it's a trick to actually do feedback. There's no feedback in these images. This is a real density of states. But you have to first know what is topography before you do this. And this is not perfect. Okay.
Sorry, just to make sure. So by atomic steps, you mean just on the surface?
Yes, atomic steps.
From time to time, there is just a step
Yes.
on the size of atom.
Yes.
Okay, okay. Yes. So it is not like completely flat. It's
Just to
just make sure.
can't do that. Experiment. Okay, good. Let's do something unpublished. Let's make a defect in this. What you find in SCT metals are these defects. This is a topography, this is another topography. You can see these atomic steps. But here's an atomic step which disappears and reappears here. What is this? I can go around here and then I'm one layer higher. So that means my crystal lattice has a screw dislocation. These are screw dislocations. This comes when you cool down the sample quickly. And thermal expansion will happen. You will make crystal defects. And these crystal defects are actually stacking for tetrahedrons. So this is a tetrahedron where at the border of this tetrahedron you have a HCP stack instead of SCC stack. So it's like this crystal and this crystal structure is rotated by 60 degrees with respect to each other. Maybe it's complicated, but not so important. Both is lead, there's no dirt here, just the stacking is different. Now you do spectroscopy on this and something really strange happens. So this is the topography, this is differential conductivity at delta 1, band 1. Here we have the peak, here we have, there seems like a gap. Superconducting gap delta 1 disappeared. Delta 2, oh, this is much enhanced here. Something really strange happens.
So once again, the color is
Differential conductivity.
differential.
So it's, I'm sitting on, setting myself on here and there. So I'm probing the two condensates, if you like.
And this is again the two bands.
Two bands.
Okay.
And you see if this defect makes a box. Who prepares this? This probably lasts for quite some time, so you can see the deltas. Yeah. So the intensity of these peaks, delta 1 and delta 2, they actually change quite a lot.
Why colors are different?
Why colors are different?
Green triangle on the left and blue triangle in the middle.
This is delta 1 at the coherence peak of the smaller gap, and delta 2 is the larger gap. This behaves quite fine. So we have two condensates. There's no interband scattering. We make defects and something happens. So what happens here is this defect makes the interband scattering. So now the eigenstates, block states, of course, are the SCC crystal, and then we have this stacking fluid. And that means the two bands will mix at that point. We have interband scattering. And we can, this is quite complicated, so I will be quick. Schupel and Scharnweiler solved this problem, Macmillan also, and others. And the two bands become mixed. They have scattering, interband scattering, and also intra-band scattering. So if I have a defect, I have like a mirror, I come with a state, scatter to another state, staying on the same band, but I can also scatter to another band. And this is all reflected in the shape of the superconducting differential conductivity, and we can self-consistently solve that. And what you see is intra-band scattering, lifetime of band 1, lifetime of band 2. And we see this same band, band 1 to band 1, band 1 to band 2, and these defects change the scattering quite a bit. And this is inter-band scattering, so scattering from band 1 and band 2, or 2, 1, and also the defect changes. So that means here, not a peak is disappearing, but actually at this defect, the two bands are coupled together to the same size of the band locally.
What's the Coherence length for this?
Coherence length is 80 nanometer. So this object is smaller than the
And
unpublished, but it will be published.
And then
submit
should I expect some kind of shift of the value of delta to
Yes,
find
I see a shift of the value. Okay, I mean you can't hardly see it, but you here outside you see the two bands, two peaks with a little bit of, and then you see that one peak here shifts a little bit to the right, then shifts.
There's a cursor various position.
Yeah, these are these points here.
And I should yes, that's a strong
So
shift.
this is on that free sample, we see the two gaps, and then they come together to one gap, shift in energy, and shift again to one gap. So
The fact that near the corners of those triangles I see no conductance whatsoever means practically that the conductivity, the superconductivity there is destroyed due to final size.
it's not zero. Zero will be black. This is
Okay.
it's not.
Near the, even near the edges of the triangle where there is also, let's say, a red point, let's say, value at the middle picture.
Where?
But like, let's say, the red spot of the third picture from the left. First, second, third, there's a red spot.
There's a red spot here.
Yeah, above. Yeah, and the same spot, but it's darker, is
Yes.
on the.
Okay, I don't have spectrum on that. So we made a line scan here, but later we repeated this on every point of different effects.
Okay.
But okay, so I just wanted to show you this data. So I think we understood this data, that the bands are not coupled, but if we have defects, we will couple the bands, and then we get one order parameter, or two order parameters will merge and make a shift in energy. Yep.
And do I understand it correctly that if I now try to go away from this defect and scan the spectrum somewhere away, I'll restore the picture with
Yeah.
two order parameters?
So if we far away here, this spectrum is very tiny, figured, but it's a normal spectrum. The conventional spectrum of the two bands per conductor with practically no coupling. So we saw from this, first of all, this two coherence peaks, which means that bands cannot be fully coupled, they have different order parameters. We saw the vortices that we can lateral displace the condensates. The normal part is holding the condensate in the vortex, and we can couple them by defects. Now I would like to come to the last thing I want to show. Hopefully, this is the last thing. This is something we are working together here, trying to make some ideas about it. So you remember this QPI, quasi-particle interference. The electron comes here, is reflected, step bench. Now we can do elastic current spectroscopy. Maybe we can do the same with phonons. So this is now more complicated. There is no theory published on this at all. There is just a private communication with a PhD student from Jörg Schwager, who has done this some time ago. He calculated the inelastic Townsend current, or differential conductivity, which has some parts which come from the electron wave function, and some parts which come from the phonon wave function. Actually, this again is imaginary real part shifted by Q. So this is just phonon traveling from the tip, going back, scattered somewhere, and going back to the tip. So these are the standing phonon modes, which should be in the inelastic current, just like the standing electron waves. Can we see that? if we see it, we have neutron scattering with SDI, locally resolved. Now our samples are infinitely extended. It's not a good thing. We need a defect. And well, let's take our defect. And we measure the differential. Yes, sorry.
So you can actually like create those defects.
Yes, they are not controllable. So we are taking the sample in a hot state and put it into the prior state. So they get a little shock.
Yes,
And they form this kind of virtual inhomogeneous.
And then you just find that. Okay. Yeah.
So this is our image. There's some electronic QPI because, as I said, the electrons are reflected. And this is at 35 millikelvin under magnetic field. So this is an enormous spectrum. And we can now measure inelastic phonic spectroscopy again, and we see, of course, the Lear-Schmidt function. But we can do it position dependent. So we have a line scattering going from outside into the defect and outside of the defect. So the outside, the Lear-Schmidt function is small. We enter the defect, the Lear-Schmidt function, so this differential second derivative gets big. We see the longitudinal form and the transversal form, and we exit this one and it goes down again. So one observation, the Lear-Schmidt function is largely enhanced in this defect. Electron form is enhanced. Why is it enhanced? Outside we have Bloch state, and we scatter from Bloch state to Bloch state. Inside we have localized states. Electrons are reflected, particle in the box, and they are separated by very large energy scale. So actually, when we have this inelastic scattering, we go from essentially the same electronic wave function to the same electronic wave function and excite a phonon. So the difference, of course, is small in energy, and the width of the quantum well state is just larger than this energy difference of the phonons. So that means we can now, we don't have this restriction anymore of K conformation, or Q. These are all localized states, and we tunnel from one localized state to another localized state on that visual form.
A little bit louder.
Huh?
A little bit louder, sorry.
Louder?
Yes, sorry.
So the bike inelastic scattering means that we have to conserve the momentum. So my electron comes, it relaxes the energy, the phonon is emitted with the same energy, but the Q vectors have to, so the momentum transfer has to be considered. So not all phonons will contribute to this scattering. Here we have a localized electronic state. There's no Q vector. Q is not a good quantum. K is not a good quantum number. No, every state can scatter into every state of phonon emission. So this increases the cross section. We get large electron phonon coupling in this box. Number one. Number two, we can map this now as a function of energy. Outside the phonon dispersion, our sample is homogeneous. So the plot here is the second derivative as function of energy. Once I go to the longitudinal phonons, I see the box. And I see a wave function. This is not the electronic wave function. This is the standing phonon. Also, the phonon is restricted in the box. And this is very weak. And once I go to the transversal phonons, the signal actually explodes. This is actually very strong. And we can see even something like a dispersion. So what we believe that this is the joint density of states of the phonons, standing phonon holes. And we map here the phonons. So this is the spatial wave function of the phonon. And you can Fourier transform this, and then you get the dispersion of the phonons. So we can do something like neutron scattering on the local scale with a supermassive resolution. So I should allow for some more questions. So I'm exhausted now, and I didn't want to tell you more. So next slide is questions. So the last part is not published. We are writing it up, and it will take a little bit of time, but we'll hopefully eventually find it in archive. So with internet scattering, condensates is almost finished, so I think in a couple of weeks it will be online, and the other stuff we're still working on. Yep.
Can you please go back to this slide with your differential conductance at delta 1 and delta 2?
We made a green triangle.
This one.
Yes.
So what you are saying that, let's say, picture number 3, in this triangle, the signal is almost absent in the triangle, meaning that there's no
delta 2.
There's no
coherence peak inside. So we are somewhere in the middle, delta 2. Let me check. The middle is here. So delta 2 should go. The middle of this is the beginning of the graph. Here we're going from here to here. So there's no coherence peak at delta 2. This is the intensity of the coherence peak. Delta 2 is 0. It goes up here. Then goes down again. Delta 2. So nothing, enhanced, and intermediate.
Then maybe I'm a bit puzzled how it can be enhanced from such a small structure if it's the single particle level spacing in this small area is quite large. The single particle.
No, this is superconducting everywhere. This is superconducting everywhere. So we are taking the. Yeah, okay. It's hard to say, but.
Okay.
So the correct way to interpret is not to look at these quasi-particle states, but to solve the BCS equations. So solve the gaps here.
Maybe I'm a bit resisting the idea of solving BCS equations in the geometry that is smaller than where the single particle level spacing is smaller than the characteristic energy scale.
No. Why you say this spacing is small?
Because it's what 50 nanometers, right?
No, there is no problem.
No problem with this.
No. Single particle spacing becomes important when you have 5 photon.
Mainly, I was thinking that because it's a clean system, I should literally compare its geometric size with the size. No. In this case, no.
No, not at all. It's different criteria.
So we need to call but I mean this. If you're interested in this, there are 3 papers which are important. So the first one is by Macmillan, who asked the question how a normal metal in contact with a superconductor becomes superconducting. So proximity effect, and it's calculated in the band structure. So there is a scattering between the normal states of the metal and the superconductor states, and this induces superconductivity in the normal metal. And the length scale is atomic. It's not. So the decay is a given phase. And Schulter and Scharnberger did an extension to this theory where they have 2 superconducting bands and interband scattering. This is the problem we solved. The full theory is by 2 Chinese guys. I forgot to put this reference, but that is to have inter and interband coupling for 2 band superconductor. And these are very complicated equations. So just a side notion, delta becomes energy dependent and complex. Even. So the order parameter becomes energy dependent and complex. And you have to separate this and solve it.
Yeah. So I have like maybe simple, maybe not so simple questions. So let's say that I'm trying to interpret your results, and you have 2 bands.
Yeah.
And when you plot the spectrum for your phonons, well, not the spectrum, but the Ashberg, if you could show that. I was thinking that if you have 2 bands, would these 2 bands interact in the same fashion? Well, not in the same fashion, but it was the same constant with those phonons? Should you see 2 different
Very good question.
combined pictures?
There are conventional superconductors, magnesium chloride is one example, where only one band comes to phonon, the other not. But both interband scattering.
Uh-huh.
And in principle, you have two Lierspach functions. You're right. For every band, there should be a Lierspach function in. Interband coupling will couple these equations. These are so complicated, I think no one actually did this.
Because what you showed looked precisely like one band function.
So in my Lierspach stuff, I neglected that there are two bands. Correct. And this is a simplification.
When you say neglect, what exactly do you mean? You just take the second derivative for your current? Am I
So an
understand?
electron from one band can create a phonon, and an electron from the other band can create a phonon.
That's right.
And I don't know, even after the phonon creation, do I stay on the same band or do I switch the band?
Exactly.
So nothing of this was included in my first part. So in this Lierspach stuff, I was just thinking in a single band picture like everyone else, single delta, everything, which is not fully correct. And I'm hesitating to redraw my own papers, but what we can show is that these bands are pretty decoupled. Even the defect-free case, you get two different gaps, and you can displace the condensers. So it means, in principle, this is a system. Okay, if you're coming from normal to TC, you have a lot of scattering due to temperature. So effectively, you have one band superconductor. But if you go really low in temperature, interband coupling will disappear, and you get two condensers.
Mm-hmm.
Yeah. So there are more implications of this. I should say that experimentally there are very few good, there's practically no data on systems like that. In theory, especially the DFT people who do superconductivity, of course, integrate all bands, all the interband and intraband scattering, they know of this. So that makes theories like mindset. And a lot of this is established, but experimentally hardly anything is known. And we are lucky to find a system where we can see something.
Yes. The concepts from one like
Okay, so that's simple. Aluminum has three electronic surfaces, but they are actually just one band which exits the first mechanism. So it's essentially one band which is extrovert. So you, I don't know how to explain that. You know, yeah. Yeah, you have one band, and I freeze this, then I get something like this, plus the whole band. So I get two Fermi surfaces, but in principle it comes from the same band. Electrophonon coupling should not be so different. So aluminum, you only see one band. There are papers that claim that there's a directional dependence of the gap, but it's very small. Niobium is more known, so niobium has two bands. There seems to be again homotopy, but niobium is typically dirty superconductor. So coherence rates are pretty small, so there's a lot of scattering going on even clean niobium, as clean as we can get it. So this seems to wash out this multi-band stuff. Lead is so clean and the coherence length is so large that we can clearly see these two bands. If you go to niobium, light is also two bands superconductor, but interband coupling is so strong that you have just one condensate. They are not separate. MgB2 is the same thing. There's hardly any example for a nice separated two-band superconductor. We stumbled across this layer just by chance. So I think it will be the future, hopefully, the fruit fly to play with these kind of parameters by defects or something. But okay, I said nothing is published. There's the PhD thesis of Professor Zlinsky. go to KIT, library, main library, or you just Google it, Microscopy PhD, you have it, yeah? So in a way it is published. But at a stage where we did not understand everything, already 1 year ago.